Good morning, I'm Doug Smith reporting for Nottingham Trent University here at the HM Revenue and Customs Centre at Castle Meadow, Nottingham, designed by Hopkins Architects in 1994. The centre's buildings are architecturally stimulating, and this morning I'll describe and explain their construction and use. Situated by the canal in Nottingham city centre, the building makes use of off-site prefabrication. Seven separate buildings in the form of courtyards and L-shaped blocks range along a curving spine road lined with trees and car parking. It is crossed by radiating streets which focus on Nottingham Castle on a steep bluff above. The Hopkins proposal won for at least two reasons besides its undoubted formal and spatial qualities. First, it could be built fast, using technology that had broadly been tested. Not a moment was to be lost, for by the time the decision was made to cancel the first project, a good many inland revenue employees had been moved to Nottingham and were housed in a miscellany of local buildings which had been taken on short leases. These fell in before the new building was ready to accommodate the people. The government faced a very large increase in the cost of the whole operation. The second reason for preferring the Hopkins scheme was that it divided the accommodation up into discrete buildings. This allows individual parts of the complex to be let or sold off as technology and government management systems change, and it facilitates phased takeover as individual groups of people become available to move in. Most of the 1,800 people who work on the site arrive by public transport. A few minutes walk from the city centre, the site is a step down towards the towpath from the town railway station and is served by plenty of buses. For the architects, the articulation of the complex into separate blocks was more than a device for helping the government extract itself from its own managerial mess. The canal, which defines the edge of the inner city and sweeps around the Castle Rock, was once lined by 19th century brick industrial buildings of simplicity and distinction. The scheme relates, as intended, to the brick-walled, grey-roofed dignity of those Victorian buildings that remain round about. These never catered for small-scale uses, but there would seem to be no reason why the new building and planning strategy could not accept local transactions at ground floor when the programme allows for them. Urban fashion, car parking lines the boulevards under the trees. The revenue buildings proved an immense constructional challenge, in which management, programming and off-site manufacture played a vital part in construction design decisions. The abandonment of the original scheme meant that vital time was lost, but the pressure to complete the project in the shortest time possible remained. The situation was further exacerbated by the presence of redundant piles, which also hindered progress on site. The Hopkins scheme consists of an arrangement of repeated blocks, which became, in effect, a production line, where specialist work groups completed tasks and moved on to the next unit. But with construction time so critical, the architects were forced to amend their original competition proposal of precast floor slabs with structural topping between concrete beams supported on in-situ load-bearing brick piers and a row of central columns, to an entirely prefabricated clear span scheme. The revised construction, developed with Ove Arup and partners, although simple in principle, presented a huge challenge to achieve the necessary levels of accuracy and consistency of finish. In addition, as part of the energy strategy, the ceiling slab was required to provide thermal mass, since the raised floor containing the building and office equipment services masked the structural floor. As so often in the Hopkins office, the practice looked to earlier schemes and developed techniques to meet the new situation. At Bracken House, in the City of London, precast concrete beams were exposed as part of the ceiling to reduce the floor depth, and in the new Opera House at Glyndebourne, precast concrete panels were used to form the soffit to the balconies and support the seating above. Here, an as-cast finish was used for a series of shallow, curved floor plates, 3.2 metres wide, which spanned the full 13.6 metre width of the building. By tying these together, and also to the in-situ cores containing the lavatories and lifts, a solid floor element was formed. The amenity building, with a fabric roof suspended from 4 raking steel masts, is placed centrally along the spine. It is both the visual and social centre of the complex, containing a multi-purpose sports hall flanked by changing rooms on the ground floor and by a bar and restaurants on the balcony above. In fact, all the non-office uses have been gathered together in a tented structure which dominates the northern side of the site. The tent is hung from 4 great masts. Its edges and those of the under canopies are propped on more slender struts. Inside, a wooden-floored multi-games court is surrounded by 2 stories of accommodation. Only these are heated, with a reception area for the whole site at the front. No visitor can be in any doubt as to where to ask for directions. A creche at the back has glimpses over lawns to a canal. The upper floor is devoted to staff eating and drinking, with a bar, cafeteria and restaurant, looking over the boulevards and the water and up onto the castle. Save for the tented amenity block in the middle of the north of the site, the buildings themselves have a strongly rhythmical structure that gives scale to their large apparent size. This, and the rhythm of the brick piers, both emerged from the client's decision to avoid air conditioning. Ambient energy was to be maximised, artificial cooling eschewed, and as many people as possible allowed to open their windows. The architects responded by making the buildings as massive as possible, but one that could be prefabricated to achieve the very tight timescale. Which is why the construction is so interesting. The piers, built off-site, are made of bricks which resemble as closely as possible those used in neighbouring 19th century warehouses, both in their slightly larger than usual dimensions and their colour. The Nottingham beds have been worked out. The architect had to go to Cumbria to find a similar clay, which they'd fired in coal-fueled kilns to achieve the proper degree of colour variation. The piers are topped by precast concrete capitals shaped to receive the ends of the precast shallow vaults that span between them. 8 full-span steel moulds were used for the long units because only the robustness of the steel could guarantee continued accuracy. 27 other moulds in both timber and steel formed the short-span units in the core areas and extended the long units as a cantilever to support the overhanging top floor. In total, 887 units were cast, of which 305 were 13.6 metre span units. Although the use of white concrete for the ceiling units was considered originally, the extra cost and difficulty of achieving a colour match with the in-situ concrete cores meant that grey RHPC with Trent Valley aggregate was used. A white translucent wash to the ceiling and the core units, rather than paint, increased the reflectivity of the concrete and achieved the desired colour match without masking the nature of the material. The mass of the brick and concrete acts as a thermal flywheel, tending to maintain an equable internal climate. The plan width was kept to 13.6 metres rather than the 18 metre norm in developers' practice. Though the narrow width does make the building frontages longer, it allows the benefits of natural light to be appreciated over a large area, and it obviates dead zones in the middle of the floor plates, which would need air conditioning. Heating and ventilation are arranged by drawing air into the building through a small duct in each bay. Underfloor fans, which can be adjusted individually, control the rate of airflow up over heat exchangers through continuous grills on the perimeters of the floors. In winter, hot water flows through the heat exchangers. They derive heat from Nottingham's efficient urban district mains scheme. In summer, cold water is circulated, which has some effect on cooling the air on hot days. At night in the same season, the fans are left to cool the structure down, so that during the following day its chilling effect can play a part in achieving an agreeable temperature in the offices. On hot days, individuals can open the floor-to-ceiling windows, creating air movements that add to the cooling of the other devices. Heat is extracted from all but the top floors of the office blocks through the cylindrical corner stair towers. These act as thermal chimneys and have circular roofs that can be raised and lowered automatically, according to internal and external conditions. In winter, on a grey day, they are scarcely likely to open at all. On a hot midsummer's afternoon, they are lifted to their full extent. They can be raised by up to a metre, causing the hot air which collects under the undulating soffits of the offices to be drawn up to the stair cylinders and expelled. The chimney effect is enhanced by cladding the stair towers in glass bricks so that the air inside them is heated by the sun. At night, the inherent thermal mass of the concrete is exploited and purged with fresh air to pre-cool the structure. At the corners of the buildings, the air within the glass block stair towers warms and rises on sunny days, giving extra drive to the ventilation system. Fabric umbrellas on tops of the towers act as large dampers, lifting to exhaust hot air and closing on cool days to conserve heat. The floor heights of the offices on the lower floors are too great for the hot air that collects under the vaults to become disagreeable to the occupants. The height and the volume of the topmost floors has been made even greater because, to work efficiently, the tops of the thermal chimneys have to be at least 7 metres above the levels which they serve. And to have extracted heat from the top floors on the same basis as the others would have made the towers preposterously tall. On these floors, therefore, the climate is tempered by volume rather than mass. They have simple hot air extraction louvers along the sides of the linear skylights that run on the ridges of the pitched roofs. The skylights have an automatic horizontal blind system to prevent excessive glare and reduce solar heat gain, but the problems of controlling heat gain on the south, east and west sides of the office buildings are much more acute, for practically all the space between the piers and the vaults is filled with glass. This makes working next to the windows remarkably agreeable, particularly in summer when half the glass in each bay can be slid behind the other half, making a floor-to-ceiling opening overlooking the treetops. But without air conditioning, even in Britain, such an amount of glass would create a solar oven if it was not modified. Several devices were needed. The most obvious is the light shelf, a horizontal plane of glass, which is placed below the springing of the vaults in each bay. Its upper surface is made semi-reflective, so the skylight is bounced off it, through a Venetian blind fixed to 45 degrees, up onto the shallow curve of the vault from which it is re-reflected and diffused into the interior by the light self-coloured concrete. The effect is enhanced on dull days by an uplighter on the inner edge of the light shelf. The lower surface of the glass shelf is fritted, so reducing by 80% the amount of sunshine that can fall through it onto the vertical glass and work surfaces. The vertical glass is also protected by the fixed metal louvers of the external balustrades that prevent people falling out when the floor-to-ceiling windows are opened. The windows themselves have 3 layers of glass, with an argon-filled sealed unit on the inside, and a simple cavity containing an elegant Venetian blind between this and the outer pane. The blinds, like the fans which supply air through the perimeter grills, can be controlled by individual users. They are designed to adopt automatically a 45-degree position against the sky at the beginning of each day, and, unless they are adjusted, they tend to make the interiors seem rather gloomy after a sunny day outside. The blind control system's default position is horizontal, while allowing people to modify their immediate environment when necessary to avoid glare. The increased transparency and light will make a great deal of difference to the normal feel of the spaces. The office buildings are capped with projecting lead-clad attics. The individual slab elements, although adopting an arch configuration, were designed as folded plates restrained from splaying at each end with a steel tie. The thickness of the units varied from 280mm at the edges to as little as 125mm on the 1.6-metre office layout module. A deep shallow line was formed between the units to allow for potential variations in deflection, although little difference has occurred in practice. Supporting the floor units are solid, load-bearing brick piers. All the brickwork on the site was pre-built by teams of bricklayers using traditional techniques. The piers were then put into store and placed in their finished position many weeks later. To allow for transportation, the brickwork was laid on bases, concrete for the ground floor and steel plates elsewhere, which had a lifting rod attached, running the full length of the unit. The floor plates, which were set on shims to produce the accuracy required, were fixed at the top of the piers. The spaces between the capping pieces and the floor plates are grouted through holes in the seating units on site. Tight tolerances were set for the work using templates, and 1,032 piers were produced and transported to the site just before being finally positioned. The office buildings were extensively prefabricated to meet a tight construction program. The local bricks of the load-bearing piers were laid in a factory, around steel lifting rods, in story-height units. They support shallow, barrel-vaulted concrete floor, spanning the width of the building. The construction of the new Inland Revenue Complex exploits techniques of prefabrication, yet this doesn't compromise the building's essential tectonic quality. Thanks for joining me here at the Revenue and Customs Centre at Castle Meadow, Nottingham. I've been Doug Smith, reporting for Nottingham Trent University. We now go back to the Arkwright building at Nottingham Trent University for the answers to some of your questions.